So good afternoon, everybody, and welcome to this series presentation about deep learning. Deep learning is a trendy subject in computer vision. All major actors in this field are proposing deep learning-based solutions or components. And one of the reasons for that is because the deep learning approach opens new opportunities in various domains where classical algorithms simply fail to provide stable and reliable solutions. So there are several kinds of deep learning tools available. And the goal of this presentation is to give you a hint on how to choose the most appropriate tool for your application. After a very short introduction about the Euresys company, I will make a comparison between the conventional rule-based algorithm method and the deep learning approach. We will then review tools such as segmenters, classifiers, and object detectors. Focusing mainly on the advantages and drawbacks, we will explain how, based on some example, how these tools meet typical requirements of computer vision applications and how to choose between them. So, Euresys is a manufacturer of machine vision components. Our headquarters is in Sorin, which is located in the eastern part of Belgium. We have R&D teams in Belgium and Germany. We also have sales and support offices in Europe, in USA, in Singapore, in China, Korea, and Japan. Currently, our staff counts 85 employees, and 50% of us are working in R&D departments. Euresys also benefits from an extensive network of distributors and is renowned for providing high-quality products and premium support to OEM and system integrators. Basically, Euresys offered three types of products. We are, of course, very well known for our frame grabbers that have been used in the vision industry for more than 30 years now. In addition to frame grabber, we also develop and produce IP cores for various interface standards and imaging sensors. We also provide a complete range of machine vision software libraries known as inVision. Those libraries are dedicated to the development of 2D, 3D, and deep learning-based applications. The deep learning term basically refers to artificial neural networks, and in particular, the artificial neural networks that are commonly used for image analysis are called convolutional neural networks. The deep learning approach offers several advantages. First of all, it reduces integration cost by allowing easier and faster application development. Unlike rule-based algorithm, where we must provide a detailed description of the object or the defect we are searching for, in case of deep learning, we just need to train a neural network with a data set of images featuring these objects or defects. So in terms of programming, since we don't have to write code to describe in detail what is considered as a defect, the development of deep learning-based application is easier and much faster. Another advantage concerns the maintenance and the evolution of such applications. So if we consider an application which detects defective products and identify the type of these defects, suppose that we need to upgrade this application to detect a new type of defect. In case of a deep learning-based application, this evolution just requires adding images featuring this new defect in the dataset, and then training the neural network with the updated dataset. And there we go. Our application is now taking the new defect into account without the modification of a single line of code. And this is probably the most important thing here, without the modification of a single line of code. If you need to apply the same evolution to an application based on conventional algorithm, well, you have to be prepared to rewrite a significant part of your code in this case. There are basically three families of deep learning tools: classifiers, segmenters, and object detectors. And at Euresys, all those tools are gathered in the deep learning bundle, which is part of the vision software package called inVision. The first tool I want to talk about is the classifier. So as you can tell from its name, A classifier aims at classifying objects or defects. Classifiers are mainly used to sort products in various classes or to detect defective products. To achieve this task, the classifier must be trained beforehand. The training is based on a set of labeled images, the so-called dataset. The performance of the classification highly depends, of course, on how representative and extensive the dataset is. Nowadays, with modern convolutional neural networks, as few as 100 images per class are sufficient to train a neural network for a classifier. After the training process, the classifier is able to classify images, which means that for any given image, it returns a list of probability that this image, this object, belongs to one of the class that it has learned. In case of defect detection, a classifier is able not only to detect defective product, but also to identify the type of defects. However, what the classifier cannot do is to accurately locate the defect itself. And this is the main limitation of classifiers. In OpenInVision, the deep learning classification library is called EasyClassify. Our next tool is the segmenter. According to the operating modes, two flavors of segmenters are available. The first one is called unsupervised segmenter, and it is used for defect segmentation. It works by learning a model of what a good product is, which means a product without any defect. And this is done by training the neural network with images featuring good samples only. After the training, even though the segmenter has never seen any image featuring defect, it is able to detect anomalies or any differences compared to the model it has learned. The unsupervised segmenter can then be used to classify new images as good or defective. In case of defective product, it also segments part of the image that differ from the learned model and therefore provide the exact position of defects. The fact that we can train the neural network with images featuring good sample only is a great advantage for application where the defective sample are not readily available. An unsupervised segmenter is also the perfect tool when defects are not predictable. For instance, in case of new defect that might appear due to the aging of a machine. The drawback to train the neural network with good sample only is that it cannot identify the type of defect because it's not aware of that. It has never learned it. The unsupervised segmenter might also not be able to detect very small defects or defect that makes the object look smoother. The second type of segmenter is called supervised segmenter, and it is used for semantic segmentation. It works by learning a model of what good product is, what a good product is, and what a defect is. And this is done by training the neural network with images that are annotated with the expected segmentation. After the training, the supervised segmenter can identify products that contain defects and very precisely pinpoint where they are in the image. So the supervised mode can achieve a better precision and can segment more complex defects than the unsupervised mode, thanks to the knowledge of the expected segmentation, of course. The main advantage of semantic segmentation is that it can basically segment anything. As long as the neural network has been trained with correctly annotated images, a supervised segmenter can very accurately segment and differentiate between several classes of objects or defects. But as always in computer vision, there is a trade-off between speed and robustness. Semantic segmentation is more precise and more robust compared to unsupervised segmentation, but it is also slower. Typically, 2 times slower for the 2 times slower than the unsupervised segmentation for the same image resolution. The preparation of the data set before training also takes more time because each image must be annotated with the ground truth segmentation. And furthermore, at least 100 annotated images must be provided per class to train a supervised segmentation. So in OpenVision, the deep learning segmentation library for both supervised and unsupervised mode is called EasySegment. The last tool I want to talk about in this presentation is the object detector. Object detectors are used to locate and identify objects, product, or defect in images. The neural network of an object detector must be trained with images where objects that must be found have been annotated with bounding boxes and the corresponding labels. As an alternative, if all objects feature the same size, clicking the center of each object is sufficient to annotate the corresponding image. And this is what we call the interest point bound. After the training, the object detector has the capability to predict the bounding box surrounding each object it has found in the image and assign a label to each of the bounding boxes. The object detector is able to distinguish overlapping objects and as such is suitable for counting them. Compared to a supervised segmenter, the annotation of the data set to train the neural network for object detection is much easier. We just require placing a bounding box around the object to be learned or clicking the center of the object. For a reliable identification, at least 100 instances of each object should be learned. An object detector is faster than a supervised segmenter. Typically, it is 2 times faster. However, of course, the object detector is not perfect. And compared to a classifier, an object detector is more or less 3 times slower for the same image resolution. The localization of objects in bounding boxes is also slightly less accurate than the pixel level segmentation of a supervised segmenter. In OpenVision, the deep learning object localization and identification library is called EasyLocate. In terms of speed, as already anticipated, we can see from this chart that for the same image resolution, the classifier is the fastest tool, while the supervised segmenter is the slowest. To further increase the speed, Euresys has recently introduced the concept of engines that represent a tool used to run the neural network. For platforms based on Intel CPU or Intel GPU, we recommend to use the OpenVINO engine. And it is particularly interesting when the inference is performed by the CPU. When the platform is equipped with NVIDIA GPU, we recommend to use the TensorRT engine. So now let's consider several types of applications, and for each of them, we will determine the most appropriate deep learning tool to use. Suppose we need to inspect small stone tiles. The application must separate good samples from bad ones. The position and the number of defects on the tile does not really matter, but it is mandatory to identify the type of defect. So to summarize the requirements of this application, we need to detect defective product. We need to identify the type of defect, and the location of the defect does not matter. So easy classified is clearly the perfect tool for this job. Another domain where the usage of deep learning tool is interesting is the food industry. For instance, before the packaging process of food or vegetables, the presence of foreign material must be detected. And for such an application, an accurate localization of the foreign material is important because we need to remove it. The identification of the foreign material is also required to understand at which stage of the process it has been introduced. So therefore, for this application, we need to detect defects, foreign material in this case, retrieve the position of the foreign material is important, as well as the identification of the material. So for all those reasons, the supervised mode of EasySegment is the most adequate tool for this application. So now suppose that we need to count objects of various types that are placed in bulk and possibly overlapping each other. We also need to identify each object. Well, if we have to count objects, identify them, and if they may overlap, this is typically a job for EasyLocate. Printing and textile industries also benefit from deep learning. In this case, the application needs to detect defective products and return the position and the size of each defect. The identification of defect is not relevant. And in these industries, printing and textile, the defects that may appear due to the aging of the machine are usually not predictable. So for this application, we have the following requirements. Retrieving the location of the defect is mandatory. Defects are not predictable, and there is no need to identify them. So because of the ability to train its neural network based on good quality images only, the unsupervised mode of EasySegment is the most appropriate tool for such application. Finally, the processing time is another aspect that should be considered. For time critical applications, the main concern is the speed. And in this case, when possible, EasyClassify should be the preferred solution. So as we have seen, there are some functionality overlapping between classifiers, segmenters, and object detectors. And choosing the deep learning tool that best fits your requirements, it's not always obvious. And in this presentation, we have provided some hints to select the most appropriate tool for your application. For a free evaluation of all the Euresys deep learning tool, we provide the Deep Learning Studio application. Deep Learning Studio can be downloaded from the Euresys website, and its usage does not require any license. Deep Learning Studio allows to create your own dataset of annotated images. It also manages the data augmentation, which means that you can artificially introduce geometrical deformation of images in your dataset, or apply color or luminosity variation, or even to add different types of noises. So the goal of the data augmentation is to make the neural network more robust to variation, deformation that are maybe not available or not sufficiently available in the dataset. During the training, Deep Learning Studio allows to monitor the evolution of metrics related to the performance of the neural network. After the training, the user can validate the robustness of the resulting neural network by means of some metrics. An explanation is, of course, provided for each matrix, as well as the expected value in case of robust neural network. Because actually we want our deep learning tool to be used by anybody. So you don't need to be an expert in deep learning to be able to use our tool. But of course, if you are, maybe you are interested to get some feedback and some metrics. Of course, Deep Learning Studio can also be used for inference to evaluate the performance of our EasyClassify, EasySegments, and EasyLocate library. So don't hesitate to download Deep Learning Studio from our website to evaluate our deep learning tool. And of course, if you need any assistance during your evaluation, please contact the Euresys technical support. And this is the end of my presentation.
So it was 30 seconds too early. We have some questions. EasySegment, how can one manage objects that were not encountered during the training process?
So in this case, if you are using the unsupervised mode, then it is automatically taken into account because, of course, you provide just good images. In case of the supervised mode, you have the possibility to retrain. I mean, of course, the object that has not been learned or the defect that has not been annotated in images cannot be detected. But you always have the possibility to retrain the neural network. So you can add new images into the data sets, do the annotation, and there you just add new images.
And for unsupervised segmentation in scenarios where the presence of defects is limited or only a few defect samples are available, what is the best solution for such cases?
But in this case, if you can provide lots of good quality images, that's fine. So for the unsupervised mode. By the way, it's also possible to use in the validation. So during the training of the neural network, you have always a validation step. During this validation step, if you can provide some images featuring defect, that's always good, because that will allow the neural network to check whether it's able to distinguish between good and bad images. So providing some defects also in the data set is a good idea. Of course, label as defective.
And easy segment, to what extent is the algorithm proficient at detecting small objects?
With the supervised or unsupervised mode?
Easy segment. I'm not. I think it's for supervised.
Okay, so supervised is very accurate. Supervised mode is very accurate, and it is during the training. If you have provided images with very small defect that has been annotated, the neural network will be able to detect them. So we can detect very small defects.
And for unsupervised?
For unsupervised, it's not working that way. The unsupervised mode is kind of limited to very small defects, so it will not work very well.
Euresys is a great company.
Thank you. Thank you.
That's what the chat said and what our people say. So thanks a lot.